Welcome. We are going to look at this problem, 2.39. This problem is going to look at deflection due to forces when you have a statically indeterminate problem. And that means you have more reactions than the ones needed to make it static, and so you need to add more information through multiple additional equations to find all the forces. Let's read it first. Two cylindrical rods, AC, made of aluminum, that one in gray, and CD, made of steel, that one that kind of looks more bluish, are joined at C and restrained by rigid supports at A and D. For the loading shown, and knowing that the coefficient of elasticity for A, for aluminum, is 10.4 times 10 to the 6 pounds per square inches, and the coefficient of elasticity for the steel is 29 times 10 to the 6 pounds per square inches, determine A, the reactions at A and D, and B, the deflection of point C. Okay, so let's first do a free body diagram of the whole thing without the supports. So we'll do that. So here we have our aluminum part, and then we have the steel part that's a little bit bigger, trying to draw it symmetrical right there. So let's give it some names, A, B, and A, C, and D. Okay, now we have a bunch of forces. So there's one thing I did wrong. So here we gotta cut here and here because there were supports there. So we have to show that there was a cut. So I'll show it with these squiggly lines. And now we have to put the reaction forces. So now, since I cut, I usually put a force that is outside of the cut. So that's going to be a force going this way. And perhaps I'll change color just to make it more interesting. How about this color? And what will we call this? I'll call this AX. Now, this is a rigid support, so it's also going to have, and actually, no, I want to do it in the direction of the x-axis, which I'm going to draw in a second. I have AX here and an AY here. And I also have a moment here at A, free moment, right? So now we want to do the same on the right-hand side. So we have a force dx, I'm going to call this to keep myself consistent. Then we'll have a force dy, and then we'll have a free moment. And I've just realized that we want to make the moments counterclockwise. Well, actually, we want to make this beam smile. So from the left side, it's going to be clockwise. From the right side, D or M about D is going to be counterclockwise. Okay, so now that we've done our reaction forces, let's draw the applied forces. So at B, there's a force going this way, and at C, there's another force going this way. And they are labeled, so we will label them too. This one is 18 kips, and this one is 14 kips. Right. Now, we have a couple more things to do. We got to put our dimensions in, so we'll do that. So we have a dimension here, here, a dimension here, and a dimension here. This is 8 inches. This is 10 inches. And this is also 10 inches. Okay, so now we can check our acronym. I used the acronym BREAD to see if I missed anything. And I realized that I didn't put my axes. So I'll put these over here. This is my X direction, my Y direction, and my positive moment direction. So B stands for body. We have a body right here, and we've included everything in that body, except for the two fixed supports. We've drawn the reaction forces here with the moments placed in such a way that they will make this beam smile, and then the x and y components along our axes. Then the external forces, we have the 18 kips and the 14 kips, and those are the only two external forces that I see. And then the axis is there, and the dimension, well, we forgot that this has a diameter of, so we'll include that, of 1 1/8 inch, and this one has a diameter of 1 5/8 inches. Okay, so now that we have this, we can check this one as well, and we can think, well, if we do the sum of the forces here, let's see what we can exclude. So if I do the sum of the forces in the y direction is equal to 0, then I can say that AY plus DY is equal to 0. And since these are reaction forces, they must be reacting to something. But there is no applied force to which they can react, which means that they are 0. So we can say that we don't need those. What about the sum of the moments? Well, we have two moments, and those are free moments, moment A and a moment at D. And again, these are reaction moments, so they react to some other forces applying a moment. However, if we don't consider the reaction forces that are vertical, the horizontal one pass through these points. And so those cannot create a moment, and the red ones do as well. So we also know that we don't have any moments. So that's good. So now let's look at the sum of the forces in the x direction. That also has to be equal to 0 because this beam is not moving, right? So what do we have? Well, we have an AX in the positive direction plus an 18 kips here, plus we have another 14 kips, plus dx. Okay, and that's it. Now we do have applied forces, which means that these reaction forces are going to react and they're not going to have a value of 0. So let's just simplify this expression just a little bit. AX 18 plus 14, that's going to be 32 plus 32 kilopounds kips plus dx, and that's it. Okay, so we have one equation and two unknowns. So how are we going to find enough information for this? Well, this is a way to do it, and that is the method of superposition. So we'll create a superposition. So let's pretend that support D is not there. So remove support D. So let's redraw the free body diagram in that way. And I'll actually also tell you something else just to speed up the process. So let's say we cut here, then we cut here, and then again we cut here once we remove that support. And actually, no, we'll do only those two cuts. So not that one. Stroke eraser, there it is. All right. So now we're going to have this support on this left-hand side. Well, we're not going to have it. We remove the support. However, we're going to have the reaction force. So we're going to say, and actually I'll remove the left support first. So let's say that here we've already proven we only have this dx, right? We don't have dy, we don't have the moment. And we still have the dimension here. and the dimension is 1 5/8 inches. And we also have this dimension, which is 10 inches. We have a force, which is 14 kips right here, 14 kips. And we have another force here, which is 18 kips. And here we have another 10. And then here we have 8 inches. Don't forget the units. Now, again, we can write an expression here. So why don't we go ahead and do that? Well, let's see. There's only forces in the x direction, so we'll sum up the forces in the x direction. And so what is that going to be? Well, the sum of the forces in the x direction has to be equal to 0. So that's going to be 18 plus 14 in the positive x direction. If we do our axis in the positive x direction, is going to be 32 kips plus dx equals 0. So we can say that our dx for this superposition, not the final answer, is negative 32 kilopounds. Okay, now that already got us somewhere, right? Now let's do these cuts that I was talking about. Let's do a cut here, right before 18 kips, and then let's do a cut here at C, and then let's include the whole thing. So we'll say this is 1, this is 2, and this is 3. So if we start with 1, with station 1, and we draw the free body diagram, what are we going to have? Well, we're going to have something like this, and this will be cut right here. So we don't have any applied force, but as we make a cut, we do want to put a P force in here. So we'll call this P1. And of course, we have our X and our Y. Here we have our length, which is 8 inches. So given that, what is going to be the sum of the forces in the x direction for this free body diagram? Well, it has to be equal to 0, and there's only one horizontal force. So we know that P1 is equal to 0, which means that what is the deformation in 1? Deformation in 1 is equal what? To the load times the length, which we do have, of 1, divided by the A of the aluminum, because that part is made of aluminum, and the cross-sectional area, which I forgot to write the dimension of in both of these free body diagrams, is 1 1/8 inches. So this is 1 1/8 inches. Same here, 1 1/8 inches. But now, since that is 0, it doesn't matter what these other things are. It's just going to be 0. So there's not going to be a deflection associated with station 1 for this specific free body diagram. Now let's go to station 2. Station 2. So we'll draw another free body diagram here. And so I want to do it in white here. And so now we're going to have this whole aluminum block. And it's going to be cut right before C. So let me make that clear. It's going to be cut right before C. So we're definitely going to have a P2 in here. Keep in mind, we also have that 18 kilonewtons of applied force and that distance of 10 inches. And this is 8 inches. Now, we have these two horizontal forces, nothing else. This is my X, my Y, my moments. And then finally, I want to put one more thing, which is the diameter, which is 1 1/8 inches. Now, if I look at this and I do the sum of the forces in the x direction, it also has to be equal to 0. And so 18 kilonewtons plus P2 has to be equal to 0, which means that P2 is equal to negative 18 kilonewtons. Now here, the deformation 2 will be P2 times L2, which is this L over here, because remember, we've already proven that this is not deflecting because there's no internal force in it for this superposition part. And now we divide by E of the aluminum times the area of that part. So we'll call this area of the aluminum as well. And now we can plug in the numbers and actually do the calculations for finding this out. And so why don't we go ahead and do that? So, hold on, I'm getting myself set up, the calculator and everything. So now we have this section 2. We're going to plug in our values. So what is P2? Well, we just found that P2 is equal to negative 18 kilo, I don't know why I wrote kilonewtons, is actually kilopounds. Sorry if that confused you. Kilopounds. So that means 18,000 pounds. I always like to convert to base units when I do these things, because then I can simplify the units and I can make sure that my algebra is correct. Now, L2 is the length over which this load is applied, which is length of 10 inches, which is our base unit for English units. So that's good. Now, EA, what did we say EA was? EA is 10.4 times 10 to the 6. So we'll write here 10.4 times 10 to the 6 pounds per inches squared. Remember, those are the units of E. And now finally, for the area, we have 1 1/8. So we'll say that that is 9 over 8 inches. And that's the diameter. So if we square the diameter, remember to divide pi by 4, because it's the same thing as having the diameter divided by 2 inside the square, but then taking out the 2, and it becomes a 4. So once we do that, and we plug in everything into the calculator, we get negative 0.017412. Negative 0.017412 inches. And those are the inches of deformation. Now, I'm realizing this video is getting a little bit long, so I'll do a part 2 and perhaps even a part 3. But this is so far what we've done. And I think you see the pattern here of where we are going. I will see you in the next video.